Okay, now let's begin lecture 23, week 8, Monte Carlo simulation applications. This is a continuation of lecture 22. And for those of you who've joined this course now, it is NE 402, Intermediate Nuclear Engineering, covering diffusion and transport of radiation in Monte Carlo simulation. I've done the introduction, diffusion, transport, and shown the similarity between diffusion, transport, and Monte Carlo. Then I went through the Monte Carlo methods, the Monte Carlo method, the underlying probability and statistics of random processes and random variables, and through a little bit of details with the Monte Carlo simulation, the procedure. And in the last lecture, I looked at applications, and we started first with modeling bare assemblies. For that, I looked at Godiva and UO2, uranium dioxide, and then discussed the modeling of a pressurized water reactor 17 by 17 fuel assembly. Mentioned a little bit about criticality safety, and today I'll be doing radiation shielding, Monte Carlo perturbation, that what does it mean? And I'll leave you with a geometry plotting exercise of something which is current research, 2020. Okay, that's my name, and that is recorded by Zain Koreshi, and my name over here, and my telephone number, personal email, official email, and personal website. Okay, let's come to radiation shielding. Now, I told you in the initial part of this course that it's very important to protect people working in a nuclear facility from harmful radiation. And everybody has got to make sure that they do not get beyond the safety limit. So there's a maximum permissible radiation level allowed. And that was covered in the first 2-3 lectures. Now, apart from criticality, an important part of nuclear engineering is the design of a radiation shield. A radiation shield you can consider is a biological shield, as well as it is a shield to protect, the first purpose is to protect the public, the workers and the general public. And another purpose is to make sure that the equipment does not get damaged to any great extent. So you need ports within a shield to put in your detectors, your wiring. So those are made, those are streams. So those modeling, those parts have to be modeled accurately as well. So on one end of shields are the light materials, such as water, which have hydrogen in them. And on the other end are heavy materials, such as iron and lead. So water has a density of 1 gram per cubic centimeter. Iron has a density of 7.87 grams per cubic centimeter. And lead has 11.3 grams per cubic centimeter. So the procedure, standard procedure is, you saw that the maximum energy transfer of neutrons takes place when neutrons strike hydrogen nuclei in water. That's when they can very effectively slow down from the MEV region down to the EV region. So in a small number of collisions, you can have a lot of energy transfer if you have water. So the first thing neutrons see is some light material, so that they are very slowly, very rapidly slowed down. And the neutrons get absorbed, they slow down, they become less harmful neutrons, they lose their energy. But while slowing down, they produce gammas through the N-gamma reaction. So those gammas which are produced, plus the gammas which are coming out of a reactor, these add up and become a bigger gamma radiation. So now, first you stop the neutrons, and then you stop the gammas. So to stop the gammas, you need something heavy. You need iron or lead or concrete. So in Monte Carlo simulation, you could be faced with a problem of, with the challenge of designing a shield. So let's look at the two extremes. Let's look at a slab of water, and let's look at a slab of iron of the same dimensions. Now, once you've done that, then you can imagine that we would be looking for an optimal configuration. Optimal configuration means the best possible combination of materials in the best possible geometrical arrangement so that you achieve the best reduction in radiation for the least amount of material that you put in. And when you're making a nuclear reactor on ground, it's okay. You don't have to worry a lot about the weight. But if you're taking a little nuclear reactor to the moon or to Mars, then of course weight becomes a very important consideration. So the lighter materials you have, the more optimally they're placed, the better it is. If you make something so heavy that you cannot carry it, then it becomes useless for space missions or where you need portability. Okay, so let's look at a 20 centimeter thick slab of water in the X direction and 10 centimeter thick in the Y and Z directions. So let's say that the front and back, top and bottom surfaces are taken as reflecting surfaces, which means that anything going back or coming front or leaking from down or leaking from the top gets reflected, and we're not going to let neutrons leak out of 4 faces out of the 6. So they're allowed to come in from the left side and go out at the right side. Now this is a modeling simplification that we're looking at to try to get a qualitative picture of what's happening. And the source I'm going to consider is a point anisotropic neutron source. Now I told you that an isotropic source is a candle. It gives out light and heat in every direction. But an anisotropic source is a torch which gives out light only preferentially in the forward direction and very little in the backwards direction. So let's say that I shine a torch of neutrons of unit strength, which means 1 neutron per second, of energy 1 MeV. And let's say it is incident on the left face of the slab, and we're going to see what is the flux inside the slab, how many neutrons leave from the right face of the slab, and so that would be the current. And then the surface flux we're going to use to multiply by a factor of neutron flux to dose conversion. And so I'll convert what's coming out into a dose in sieverts. And then we'll see whether the radiation is less or more than the permissible. And let's see what kind of reduction has taken place. Okay, so let's start with water. Now, let me give water the material number 3. And so water is H2O, so hydrogen is 1001 is the ID. Oxygen is 8016, 8016. And you know that water molecule has 3 atoms, 2 are hydrogen, 1 is oxygen. So the atomic fraction of hydrogen is 2 out of 3, which means 0.666667. And the atomic fraction of oxygen is 0.33333. Now, I take a material number 90, which is pure hydrogen, because when I want to look at the gamma production in hydrogen, I know that oxygen is not going to produce gammas to that extent. So I'm only interested in the gamma production in hydrogen. Similarly, I'm interested in the gamma production in water. So I can look at 92 material as well as 90. So here's the physical scenario. That you are standing in front of a CF252 source, which has an activity of 532 curies per gram. So CF252 is a very powerful, intense neutron source. It gives out a neutron dose 22 sieverts meter square per gram per hour, and a gamma dose of 1.6 sievert meter square per gram per hour. Okay. So, so if you have so many grams, so many hours, and you have a surface area of so many meters square, then you can use that conversion to get how many sieverts are coming out. Now let's say you are allowed a maximum of 5 rems per year, which is 0.05 sieverts per year. And you're standing right in front of it, you're standing in front of 1 gram of CF252. Now 1 gram would be less than what you get in a teaspoon. So if you have less than a teaspoon of Californium-252 source, and you're standing for 1 hour in front of it at a distance of 1 meter, then from these numbers, you have already accumulated 400 times more than the annual limit that you put. So what's the way now? Now you have to design a shield. You have to put the shield between you and the neutron source, just like you were standing in front of a heater and you'd have to put something in between so not to receive so much heat. So consider a 1 MeV neutron source for which a water and an iron slab are compared, each of thickness 20 centimeters. Now results from the MCNP simulation listed below in the table, I'll just show you. They show that the total neutron dose across the iron shield is about 100 times higher, while the photon dose is about 3% less than that for a comparable water shield. Now, I carried out MCNP mixed mode simulations. So you can run the Monte Carlo simulation for neutrons only, for photons only, and the third way is for neutrons and photons together, because photons, which are gammas or X-rays, can be produced by the N-gamma reaction, can produce gammas. So again, let's look at a 20 centimeter thick times 10 by 10. So that's 2000 cubic centimeter, which is about 2 kilograms of water. And the same volume of iron would be about 8 times more, because the density of iron is about 7.87 times more. So 2 kilograms of water compared with 16 kilograms of iron, which is more effective. So first, let's look at the neutrons coming out of CF252. Now what you see in the left column are the tallies, and what you see in the second column are the surface for a current tally, for a cell, for a flux tally. So let's look first at the current of neutrons coming out of surface number 2, which is the right surface of the slab. And we've got the tallies broken down into 2 energy bins. The first bin is the low energy bin, 0 to 5 electron volts. And the second is a high energy bin, 5 eV to 14 MeV, everything lumped in. Now, what you see is that the high energy bin from water is very low, but the low energy bin is higher, which means that water is very effective in slowing down the fast neutrons. So you can see that only 3 neutrons out of 1000 would leave from the right phase, while only 2.3 out of 100. So 2% of the slow neutrons would leave, and about 0.3% of the fast neutrons would leave from the right side. So this slab has a transmission of about 2.64%, and the relative error of the tallies says that it's a result which you can say to 1% confidence, but it's okay. Now compare this with what you would get from iron, which is the second row over here. So iron has a much smaller low energy current, but the uncertainty is 29%. And in the high energy bin, it's much higher than what it was for water. So iron lets out about 23%, while water lets out about 2.6% from the right phase as a transmission. So hydrogen and water are much more effective than iron for shielding a neutron source. Now let's look at the F4 tally. F4, F14, F24, 34, 44 are flux. Now the cell flux, you can see water is 10 to the minus 2 at the lower, and the lower energy bin 10 to the minus 3 in the high energy bin, average of 1.72, 10 to the minus 2. In iron, the uncertainty is much higher, but the estimate is also much lower in the low energy band. And at the high energy, you can see that the flux is much higher in iron. So the flux in iron is much higher than that in water at the high energy. which means that it has not been effective, as we saw before, in slowing down fast neutrons. Now let's take a surface flux F2 on the right surface, multiplied by a flux to dose conversion rate, and let's see how many sieverts come out. Now this number is sievert per neutron per second. So if you had 10 to the 12, then you would have to multiply all these numbers by 10 to the 12. So, and sievert, you saw that you're only allowed to have 0.05 sieverts in a year. And here you're talking about standing in front of it in minutes at the most. So you can see that 10 to the minus 15 sieverts you get from water, and from the dose in iron is much higher. It's 10 to the minus 13. It's 100 times higher. So again, goes to prove that iron is a bad shield for neutrons. Now, if I use a tally multiplier, FM, to multiply the flux, then I've got -1 means that, in this case, -1, 90, 102. 102 means the reaction ID. This is the N-gamma reaction, which is the radiative capture reaction. So for material 90, which is pure hydrogen, and -1 means that multiply by the atomic density of hydrogen. So you get this result of 10 to the minus 4, 10 to the minus 6, added up to 3 times 10 to the minus 4 for the N-gamma reactions in water. Now, similarly, you can see the N-gamma reactions in iron are 100 times less. So water was good in attenuating or slowing down the neutrons, but it was bad in the sense that it produced gammas. So it was a very effective neutron shield, but it produced gammas, so it added to the problem of slowing down photons. Okay, now let's look at without the -1 sign, so let's not multiply, so these two are the same, so I won't discuss that. Now let's come to photons. When you come to photons and you see that F11 is like the F1 tally, so 1, 11, 21, 31, and so on, represent a current. When you have a P after the colon instead of an N, then you've got a photon current, a gamma current. So gamma and X current and X-ray current across the right surface, surface 2, you can see at the low energy bin, there's nothing coming out, no photons are emerging, because photons are energetic enough for them to be able to transmit, to be able to come out on the other side. So you can see that for water, about 17% photons come, while for iron, about less than 1% come. So this goes to prove, and this one too, which is the dose, that iron is a much more effective shield for gamma radiation. Now here I've got the numbers added up. For water, you can see that the neutron dose is about 100 times less than it is for iron. Gamma water is not good, it's bad. So that's what we discussed, that we are going to use iron. So conclusion over here is that this is a MC application for the total dose across the iron shield and the water shield, and you can draw your conclusions that you have to carry out the simulation separately for water and iron. Now let me show you this table for what is called the half value thickness. So engineers need a rule of thumb that roughly how many centimeters do you need of any material to reduce something by half, to reduce radiation by half. So that amount of material is what we call the half value thickness. So from here you can see that I've taken this data from the nrc.gov site for the attenuation coefficient, the mass attenuation coefficient, mu over rho. So I estimated the half value thickness. For water, it's about 10 centimeters. So 10 centimeter thick water is what you need to reduce the radiation intensity by half. Now, instead of water, if you use concrete, then you would use half of that So 4.5 centimeter of concrete is enough to stop, to reduce it by half. And that's why concrete is used in nuclear reactors. And iron, of course, iron would be expensive, concrete would be less expensive. So iron is 3 times more effective than concrete. And lead is, you can say, almost twice as effective. So the best shield is lead, second best is iron, third best is concrete, and water is not such a good shield. Okay, now that was for shielding, and you can do big problems for radiation shielding, and for big problems usually Monte Carlo simulation is used because you can model the ports that are necessary for putting in instrumentation. There are streaming ports, there are L-shaped ports, there are ducts, and there's so many things in a shield. You cannot isolate a nuclear reactor core from its instrumentation. So you have to have wires and things going in and out, sensors. Okay, so that was the topic of radiation shielding. Now let me take you to Monte Carlo perturbation, which we'll see in the next 10, 15 minutes. Monte Carlo perturbation. Now, perturbation, what does it mean? It means a 5 or 10 or 15% change in something. Now, whenever you want to make a best possible design, you have to run a simulation many, many times to see what is the best. Now, Monte Carlo simulation takes a lot of time. So if one problem takes you 2 hours, then you would not like to run it 100 times because that's 200 hours. So you would like that in one run, you should be able to predict that if you make little changes here and there, then what would be the effect of those changes? So that is done by perturbation theory. And you saw when we were in college, you saw that if you know what a function is, you can obtain its first derivative and second derivative. You can put it in a Taylor series, and you can estimate. For example, if the function is x squared, then if x is 2, then y is 4. Now I ask you the question, what is y if x is 2.1? So you can do the calculation again, or you can use Taylor series because it's only a very small change with respect to the reference. Now for small problems, it's better to solve them again. But for big problems, it's not better to solve them again and again. So what you do is that you look for a theory, a perturbation theory. Now let's see that if we do have a perturbation theory in Monte Carlo, which we do, then how do we use it? So as I discussed in the previous lectures, that there are deterministic ways and there are stochastic ways. Now in Monte Carlo, we've got 2 methods. We've got derivative sampling and correlated sampling. In the deterministic case, we've got the adjoint weighting in a Lagrangian variational formulation. So these are the 2 separate routes. So let me talk about the stochastic route, that in Monte Carlo, how do you estimate design changes? Design changes could mean that supposing you have a mixture of water and iron, and you want to know that should I mix 60% of water, or should I mix 70% of water, or should I mix 80% of water? Now these are the little design changes that you would like to study, the effect of these changes. So again, let me go back to the simple example of Godiva. Let me try to understand on Godiva. So what I did was I did a Monte Carlo simulation using MCNP for Godiva. And I took 1,000 neutrons in 130 cycles. And 30 cycles I skipped for reducing the effect of fluctuations on my statistical accuracy. This is a good practice that just leave the first few bad cycles until it stabilizes, and then you can get a better result. So this figure over here has one x-axis on which we see the relative density, which is rho r, which is rho divided by some reference density. Now the reference density for Godiva is 18.75. grams per cubic centimeter. So let's carry out several runs. Okay, so for the reference case, when the relative density is 1, you can see that K effective is 1, the left y-axis. And on the right y-axis, you can see the current, which is the lower curve. So the current for reference density is about 0.58 or something. Now the question is, if I increase the relative density or if I decrease the relative density, then what is the effect on the system multiplication K effective, and what is the effect on the current, the transmission from the other side, from the Godiva sphere. So you can see that first I did many runs, and I saw that when Godiva sphere becomes more and more dense, then the transmission becomes less and less, while its multiplication becomes more and more. So more density means supercriticality. Less density, less than the reference, means subcriticality. And the inverse is true for the current. The current becomes more for less density because now the neutrons have a greater chance of escaping. And when the density goes up, then transmission becomes less. Now let's see how would I do it exactly. So let me take again the simplest deterministic expression for K, which is the production rate divided by the loss rate. The production is by fission, so sigma F times phi is the number of fissions, nu are the neutrons coming out per fission, so nu sigma F phi is the number of fission neutrons being produced per unit volume per second. Down here, we've got all this multiplied by phi. This is the leakage term, d del square phi minus d del square phi. This is the absorption term. So the production divided by absorption gives you the system multiplication. Now, if I write a Taylor series over here, and Taylor series means the new value is equal to the old value plus the first derivative times the change in the independent parameter times the second derivative times the square of the change in the independent parameter. Then I can get exact expressions for the first and second derivative from this equation 10.1. And these are all numbers apart from the row. So I can very conveniently, for the reference density of 18.75 and for the cross-section data for one group which I've taken from words, I can estimate the derivatives, the first and second derivative. You see, so I've got such a neat Taylor series. And if I put these in, then I can predict that what are the values. So this is called, these are the derivatives. I haven't sampled anything as yet. So this is just an exact expression. Now, so I'll plot these curves that you can see, and basically the blue circles that you see down here represent the relative error in the reruns. So they go like that, and randomly they stay like that. But the green triangles you see is the relative error in the perturbation, and that goes like parabolically almost, that as you increase or decrease, then as you go beyond a certain limit, the errors begin to rise, which tells you that perturbation theory is accurate, as you would expect, for small perturbations. So by this, you can see that what is the band within which you can operate, within which you can predict using perturbation theory. So for example, here you can see that I can go up to 40, 50%, 60%, and a reduction of 60%. So that would be the relative error. So this is how, well, MCNP gives you the derivative samples, and that was for the K, and similarly you can do for the transmission. So, so that was very useful, that you can apply Monte Carlo to get first and second order perturbation changes. Now you have to specify what your perturbation is and which region it is in. So what the simulation will do is it will, while it is doing the simulation, i.e. it is, for example, for a track length estimator, if you are updating the distance between collisions, then at the same time, you are sampling for C and T in what I showed you in a previous lecture, that K is equal to CT. So you get an estimate for the perturbation. And so you get an estimate for, because you can have an exact expression for the first derivative and second derivative. So yes, you can sample for the derivatives in a single run of MC, and you can use it for small perturbations to help you in optimizing your design. And this has been used for many, many problems, and I'm going to show you 2 or 3. One of the problems is in shuffling the fuel so that you get a uniform distribution. So you can do genetic algorithms, or you can do perturbations of MC to see that should you remove a fuel from here, does it reduce the K effective? If it does, then increase it somewhere else. So you bring the K effective up by the same amount while changing different amounts of fuel. So this way, can you minimize? Can you keep a reactor critical for minimum critical mass while preserving the system multiplication of 1? So that's another very interesting problem of minimum critical mass. The first person to give that was probably Goetzel in a very early paper. You can see that Goetzel said that there is an optimal distribution of fuel by which, and he did it for reflected systems. So there are exact analytical expressions in 2 groups for Goetzel's optimal distribution. So you can do it for that. You can do it for designing optimal shields. You can use Monte Carlo perturbation. You can use it for working out the best density of a control rod. So, you know, there are so many design parameters that you can vary, independent design parameters to obtain an optimal design. Okay, now this picture shows you something similar to a Gen 4, a Generation 4 nuclear reactor design concept. This is the 4S type of a core arrangement, super, safe, small, and simple. So this is the Toshiba design, 30-year reactor, which is a fast reactor. It has up to 20% fuel, enriched uranium, and it's got molten sodium, it's got electromagnetic pumps, it's got a passive safety system, it has a control rod which falls under gravity, and the first 15 years of operation, it runs by gradual upward movement of the control rod. Now, so it has enough excess reactivity at the beginning of cycle to let you operate it for the first 15 years by just moving the control rod up. The next 15 years, it moves the reflector up so that to better economize the neutron population. So these are the 6 or 7 Generation 4 designs which are being considered. So, so you should try to model the geometry of this. You see the hexagonal regions which repeat. So, and there's an outside reflector. So try to do this exercise. Now, another another modern new development in nuclear reactors is what you see here. Now, this is a micronuclear reactor. So if you look at the dimensions over here, so it's about 35 centimeter radius, very small nuclear reactor core, applications in nuclear space. As I said, that here you want to minimize the weight of this reactor so that you can take it on some rocket to Mars, and you can, if Mars is inhabited, then it can produce power. It's also for underwater systems. It is based on concepts from early space missions, and it is a new design by Westinghouse for designing its eVinci reactor, which will be low power but transportable, modular, and factory built and you can just take it on a big trailer to wherever you want it. So it's got very specialized applications. But let's look at this design because I want you to be able to model this. So what you see over here, this picture is from the top and this picture is from the side. So this is a plan view, that's an elevation. Now this is a barrel, it's a monolith. So inside the barrel, there's a hexagon. The red ones are the fuel rods, which could be uranium nitride, 70% enriched. The blue ones are the heat pipes, because this one does not have pumps, it does not have moving parts. So a heat pipe is another concept by which a liquid becomes a vapor and goes up, carries the heat away and transports it. So, and then you can use either Stirling cycle or thermoelectric generator, whatever. So here you've got to design a hexagon with hexagonal cells, and these are the green is the reflector, the yellow is something strong which can withstand the heat, niobium, something strong. So, and heat pipes have some liquid metal like liquid sodium, liquid potassium, liquid sodium, potassium, and there's another. So you can look at various liquids which can operate at high temperature. Now, here you see rods, control rods, which can be rotated. So if you don't want a lot of absorption, you can take this rod back. So these are B4C, boron carbide rods. Now, the way to design these is first to work out the surface coefficients using the mnemonics. And this is how you define the planes. I think I'll take you through a whole one lecture on an input file, how it's made. But roughly, this is how you have the control rods, which are cylinders. That's the material number, material density, the bounding surfaces, the importance. I'll talk of all these things when we come into how you make an input for a simulation. These are the plane surfaces, top right, top left, top and bottom. So when you've made the surfaces and the planes, the third step is to run MCNP in the input and plot mode. So these are the commands for without running it or processing the cross sections. This is the command MCNP5 IP, input is input file. Then you're asked for inputting your command. So plot, here I plotted the picture perpendicular to the Z axis, extent like it goes 35 centimeters left and 35 centimeters right in this square. It labels the surfaces. When it's 0, 0, it does not label either surfaces or cells. It gives different colors. So this is the plot when I did not model the hexagon inside, only the outer regions, because you see the sense of each surface is very important to define the cells. And here we make mistakes, most of us, because we get the sense wrong. Is it left, is it right? So you have to be very careful. So making a geometry, you have to go step by step. So I first worked on the outside and then I worked on the inside. So you can see that a lot of effort has to go into modeling the inner core and the outer regions. So I leave you with this and end the lecture over here. These are some problems for this lecture, that whenever you're doing a simulation, use things, it's like swimming at the shallow end before you go and take a jump in the deep end of a pool. So this is the shallow end problems number 1 and 2, easy problems. And number 3 is where I've given you a very practical example of a U235 sodium fast reactor. And what I would suggest is that you write your own little simulation. Fast is easy. Imagine that it's got no thermal group. So just try to simulate over here. And question number 4 is calculate the K effective of Godiva using fast reactor 1 group cross section, which I've given in this book in the earlier lectures. Question number 5 carry out a simulation to determine the albedo of a graphite slab, again with MC. Question number 6, compare MC simulation values for K effective values of some fast critical assemblies. These are given in Bell and Glassstone Nuclear Reactor Theory, page 247. So these are the kind of benchmarks that you can do to get confidence in Monte Carlo simulation. So I hope that to summarize in this lecture and the previous, I've covered some applications of paired assemblies, of a PWR fuel assembly, of shielding, of storage of fissile material and solutions. What is the importance of that and why would you do that? And then I've shown you the geometry, especially because geometry is such an important part of the simulation. And that's the strength of Monte Carlo, to be able to model irregular geometry, the kind of world that we live in, where everything is not a slab or a circle or a cylinder. So this models geometry through Boolean algebra, combinatorial geometry, and that's why I gave you 2 examples of 4S and a micronuclear reactor like Evinci. So these are very good practice problems, and I hope that you have understood most of this. So I'll carry on some more applications in the coming lectures.